Professor Anagnosto apologized that he cannot attend the conference. Therefore, I will present the research works at our group. So, yes. The research, the chair of underground construction, focuses on 3 topics: the swelling of untreated rock, squeezing ground, and tunnel face stability. Let us start with swelling of untreated rock. Swelling is the phenomenon where certain rocks increases its volume due to water uptake. In the case of untreated rock, it is mainly due to a chemical reaction, more precisely to the anhydrite to gypsum transformation. And the macroscopical observations of this phenomenon in tunneling are, for example, the floor heave. You see on the left a case of the Kimbeck tunnel, where we have observed 1.5 meter in 3 months floor heave, no? And in the presence of a lining, the rock will exert a pressure, swelling pressure, which can exceed the bearing capacity of the lining, leading to damage, serious damage, as you see here on the right, the Belgian tunnel. No? Now, this swelling has caused several damages on a lot of tunnels in the past, and this damages has been observed since more than 150 years, but it is still an unsolved problem. Now you see in the bottom of the slide recent examples of tunnels where rehabilitation or maintenance measures were needed. Let us start on the left, the Belgian tunnel. You see the 3rd tube, which was necessary to be constructed in order that we are able to close the other 2 tubes sequentially, tube 1 and 2, and repairing them, because otherwise we must stop the traffic, and that was not allowed. So the cost of this additional tube amounts to 500 million. And current ongoing rehabilitation works in the Engelberg Base Tunnel in Germany, the cost of them amounts to 140 million francs. And we see on the right the Kimbeck Tunnel, the cross-section of the Kimbeck Tunnel. It shows it has a critical stretch with a length of about 100 meters, where we have active swelling. And so from time to time, some rehabilitation measures, maintenance measures must be done due to this swelling, no? And the average cost amounts to 0.5 million per year. Now, the reasons for the construction setbacks is definitely the very limited knowledge about 2 issues. First, the mechanisms underlying swelling, no? Which is a very complex chemical reaction in addition to transport processes. And also the macroscopic behavior of the rock. The reasons for that is even at the scale of laboratory specimens, no, we need a long duration for swelling tests. In other words, for the anhydrite to gypsum transformation, in order to achieve an equilibrium, so that no more observations will be done. So long duration. At the scale of laboratory, we are speaking of years to decades. And on the other hand, we saw the picture before. I forgot to mention that this is a picture from the gypsum Kuiper. Probably you remember. I go, oh, it was too fast. How heterogeneous it looks like, no? So at laboratory scale, if we want to investigate this systematically, we will need an extraordinary big quantity of tests of which are extremely time-consuming, and therefore, in literature, you seldom find systematic information regarding the swelling of anhydritic rock. We started 10 years ago a series of tests. We construct for this purpose this type of frames. Details regarding this type of equipment and all some of the equipment I will show in the slides, I will explain it more details during the lab visit. No? And, well, in view of these experimental difficulties, no, we started also, or we decided to study the fundamental mechanism underlying the anhydrite swelling. More precisely, for example, the thermodynamics and kinetics of anhydrite to gypsum transformation. You will find the results in the PhD thesis of Serafimidis. On the other hand, the experimental investigations of Dr. Wanninger, which aim to quantify the chemical-induced strains both in natural rock and artificial rock specimens, no, made necessary the development of new testing equipment and setups, which I will show in during the lab visit. I want to emphasize that all this new equipment were conceived, designed by ourselves and constructed in our workshops. No? They are specialized tests. No? And also I want to mention the ongoing work of Mrs. Nussio related to coupled chemomechanical modeling of anhydrite swelling. Well, besides this fundamental research of anhydrite swelling, we investigate and propose a new method for controlling, or as rehabilitation method for controlling the swelling. I call it artificial ground heating, because it is, from the implementation, quite related to artificial ground freezing. No? The goal is to heat the ground, not to freeze the ground, but to heat the ground via pipes, not freezing pipes, but heating pipes. The reason is because we know from thermodynamics that we have a transition temperature of 49 degrees. From in situ temperature of 12 to 50 degrees, going to 49 degrees, the solubility changes, and therefore also the rate of swelling will change. So at 49 degrees, no reaction will happen, so the swelling will stop. No? That will be the first case where we, instead of acting against the symptoms of this disease, we are combating the cause of the disease. That is the first, will be the first case. Well, the technical feasibility is given. We know how to do that. No? The economical feasibility is the problem, are the cost. We calculate the cost for this. Again, it is not a huge, the whole Kimberg tunnel, we are speaking of a stretch of 100 meters, 80 to 100 meters. And this, we calculate the required energy, and we obtain 1.5 kilowatt per meter for this stretch. If we compare it to the annual cost of repairing the Kimberg tunnel, it amounts only to 35%, so we are saving money. No? We are not, we don't need to do something else. That is also the advantage. And in addition to that, we also propose a question, what happens if we, instead of heating to 49 degrees, we heat only to 45 or 40 degrees? No? And that is, has been investigated with new tests. The first one, thermal control swelling test. No? I will show the details during the lab visit. The results are very, very promising, because we can slow down extremely the rate regarding to the time life of the tunnel. No? So, let us continue with the next point, squeezing ground. Squeezing is a phenomenon of large deformations we observe in tunnels, which are caused, firstly, due to because we have very weak rock, fault materials. Secondly, deep tunnels, it means high in situ pressures and the presence of water. These three conditions. You see here the case of the exploratory tunnel of the Gotthard motorway tunnel. And squeezing, it is due to these conditions, it is not surprising that we found it, or it's a key issue of deep tunnels, deep alpine tunnels. Indeed, it was the case of the Gotthard base tunnel. The key issue of this tunnel were not the 57 kilometer length. It was the 1 kilometer length of the north part of the Traversa Intermediate Massif. That was a key issue of the tunnel. Without solving that, no tunnel could be constructed. No. And therefore, during the planning of this part, that triggered the research at the chair of underground construction since the 90s. That is the time of Professor Kovari. No? And furthermore, we were involved in other projects where also squeezing is a key issue, as for example the Gibraltar Strait Tunnel. You see here these two green sections are paleochannels, which are filled posteriorly with breccias, which are normal consolidated clay with hard inclusions inside. That is extremely demanding for testing. No? And what also a particularity here are the 500 meters water table. So we have very high water pressure. Now, therefore, in summary, investigating squeezing demands on mathematical models, obviously, and also experimental work must be done for knowing the mechanical behavior of this material. And that led for us to the design and construction of a new triaxial cell, which I will show with specific capabilities. Cell pressure of 250 bars, pore water pressure of 30 bars, etc. No? And several works were done in this context, and these results can be found in the different PhD works. For example, Vogelhuber, who modeled constitutive the Kaki-rides of the Gotthard base tunnel, considering pore water pressure. Ramoni investigated the jamming of tunnel boring machines. Now I must look. Cantini, the special effects around advancing tunnel phase. Then Vrakas, the consideration of geometric nonlinearity with regarding large deformations. Then Donk, constitutive modeling of weak formations, more specifically the breccias of Gibraltar, considering also high pore water pressure. Metzger, the modeling of heterogeneous anisotropic squeezing rocks. Then now we have the ongoing works of Leone and Verdekemper. Leone, specific time effect. He work is regarded to time effects, more specific creep and consolidation. And Verdekemper, phase extrusion and stability. And finally, since 6 years, we investigate the behavior of the so-called Opalinus clay. Opalinus clay will be the host rock for the Swiss radioactive waste repositories. No? And that demands a constitutive modeling of the Opalinus clay, also coupled thermal, hydraulic, mechanical tunnel design analysis. Now, let us come to the last point, tunnel phase stability. Tunnel phase is a part of the tunnel where excavation takes place. What happens if it is unstable? It is clear. You see here an example of the Kimberg tunnel, 2002. By the way, this event triggered the swelling in the Kimberg tunnel. It started after this happened. No? And yeah, which are the consequences? Unstable phase, it is obviously a severe obstruction of the tunnel advance, no? And it requires very costly and time-consuming remedial works. No? So it must be avoided. And the research in this field, it started at the time of Professor Kovari in the 90s. No? The motivation was several construction setbacks experienced in a large infrastructure project. That was the reason. And the chair at those times was involved in these projects. No? In these periods, 25 years ago, Anagnosto and Kovari developed a method for assessing tunnel phase stability, which is used today widely almost in every tunnel worldwide. No? Almost because the tunnel projects are constructed under increasingly more difficult conditions. You see here in the case of Storebælt, Denmark, tunnel in Denmark, the water table was 5 bar, no? In the glacier Thiel. And in the Lake Mead, another project where we were involved, the water table is now 140 meters, no? And, well, it triggered also more research works. For example, the work of Roberto Schurk, PhD thesis regarding the stand-up time of the tunnel phase, or the one of Sarah Sink regarding the stabilization by advanced drainage. And this water table increases now with Gibraltar Tunnel with 500 meters. And here, again, the key issue is the technical feasibility of crossing these paleo channels. So I come to the end. I want summarizing, what can we say? That the research was and is motivated, as the chair, no? Was and is motivated by new questions which arise in the framework of cutting-edge world projects. That is, it can be said so. And what we can observe, we have very different projects and questions which arise, which are regarded to the different depths, material quality, water table, for example, but unify by again and again the same fundamentals and principles in mechanics. That is the way how we deal with that. No? So that's all. Thank you very much for your attention.